calling ambulo. Whatever we do, Jioni safu nola with whatever we do. Hale yide munyu skula, nyepamne ne kudlukula. Nyepangi ragala gena, nyepamne ne kudlukula. Ibuloke nongoto ni beti sola. Ibuloke dato ni betoto.
Bege Congo.
Lamin.
Na?
Lamin te jibe norin te nyame Lamin.
Kabana wulo kono.
Wulo kono tay mo Lamin.
Pa bilenki.
Muna ngata afamole.
Haina.
Ngata. Ngoto le. Fabrama.
Mingi. Baba nyola.
Ngoto le Fabrama.
Namu jumara kan kuma diten.
Fabrama.
Jumara mu.
Ndele bare muso.
Lunda mana. Jamani bere.
Lindo ko.
Jamani.
Bari ngoto man ko.
Bari jamani fana na ramudu wa kontan.
Ngoto minaka ngala min de fon filitala. Lamin jibe nori nyala.
Lamin ila siran sama ne benki. Yala so tol sayni no ko mo lokko momo.
Ngoto.
Nam.
Itedinte yalo ne Lamin hakilo diata bake karambu ngoto. Anu santeng ministry ko di ngole si suko na amanke ko do holiday
si bitun
bagona de
ala ni ko kede namo balo
ala ni na ko na karta bulo be dam ala ni je
ngodo
nam
ngoto mon kontan feren
jamani mu ne keda
ifike Lamin ki wulo ko no nyintay mon ko do fete malo Lamin nyande sila la be la moy kala karango
jamani karamu wol be soron ne ko fasita wulo ko nako
karambu wol ma soron ni ko karamu wol soron da amanke ko holiday lem ngodo dindi wo nyanta sila la ala karango la moy yamen kamen fue man kontan anda mande
alla nyin kombo courant adanda la kombo len do la jankara mol soron do kamen courant ma ra do la kombo e ko ndol fana na kara mol soron je kara mol soron Lamin ada lo nyino la man tara fe na sokon ala mu nekela
Lamin ite fete malon ko lesinol be ke kar radio to
nga fine
e ko yana di mo Lamin
nga fine
ya mu na fonye
bi kabin mina kan tambita nteri maning Fatu tambite la sukol ala diningol bebe siri be la moyka
faru dan so am fana tambita jele ni subala la ngaje diningol be jet talanta nen kili waro e be seri jelet
sa Lamin fanante ku kili ko keno la ba Lamin bita ka wulo ko no nyinta mo Lamin
amandara fenela
ite dine ko di man si yakaru lesino la moy radio to e balon na
mu ne ka ke afende ba nyaara ni alon
telentel jikot
afende ba mu ne be ke
ite balon tel be jikritel ni man karambe ku kele yaje nata karana mbasa mala ya itarije
par ñarande kombo courant ho findira kombo ide na rajede ni sonka bay ko Lamin manya tala wulo ko aru karam wolbe so da fa ñembe
ko to wole nati bawo ngalle ni Lamin kuntala kombo courant o ka fa me kombo courant asototal wala kinay ko e sisu ko no bari ni ko e sisu ko no be karangol di ke la radio ni telel to hani tele masoto to nyaay man tele bar radio be bulan ko to batiri sanga ay si ay alamo
sa do kala nyaadi
ko ta o bulaji
ado kala nyaadi
kamun ke nyaadi
radio be wala moy la be mona falaje
ibe la karandirol kala jele
ti talle be radio ko men ka karande
ile subject ro baby jele baby jele
wala nanga coco moy fa dan so wolya ngombe tambi kana ngadi ni wolje be ikadum bungo de ko kada ma
asototal de
Lamin mala be karawala de
bari laftalal ideal on ko inde every year second wala fourth
muna ni ko di ha ko nde ko folle sinila mba ndele sinilo ne ba
mba foke en koto wole fango yen wulindi yalo famo keta bat yu fana bulata ko ko me yen nati jambi Lamin nyanta karana ntel be jiko be nyineka ya bulay kara wulo kana ta kilar ya bambalo yo be bulaje koto dindi ngoy si ayala le sino la moy radio
wala ka munda karam mo man soro Lamin nyanta kara si so na radio
la sila le ayala le sino
dal ko korno ko smolo
kilar ya
be ngala ko momo sa mi do ni ko no kera
mengi bruzo
ndebe ko do la ba rosa no radio ba no bari woro radio ni abe jele ba do ngamra do man dembe buljan dala nyara nyar wofra bu ko fendi mo la Lamin tayra ba rosa
bara te ku folo ajibe nori nya labi tamete ku
teku
bari ko do famo ke
imagine nani nyambol si zol le keje kisigi man si zol no le kafun ka nyoma bari nyambu kilo ni manya na kafinde ni nambe ko zol la ga
ngalle limbeta de be nyambo do dilanna
nyara ni ko ridin fennat nyara nata
bari famo ke da
ngata bungono tammi bungono nyara ngando ko fele ko ke e baru nganda ni pelo landi jak
iyo awa betar la
bungono bismillah bisu diara
pendulala ye fongo tanka sina dolu tanka korota korota
Hello, viewers and listeners. My name is Samuel D. Kwede. I'm here again to continue our discussion on photoelectric emission or photoelectric effect. This is physics, could be relevant for grade 12. From our previous discussion, we said one of the important challenge in the 19th century was the behavior of light. And we had a problem with that. We needed to investigate how this light actually behave. And we saw from Planck's experiment that the energy of the light after the black body radiation, the energy of the light was, he said, was directly proportional to the frequency of the light. So now we have to go much more into that and see what happens when we penetrate light onto a metal. The process by which electrons leave the surface of metal when light is incident on that metal is what we call photoelectric effect. The emission actually is what gives the effect. So to see this effect properly, it has to be a UV light, not light of all frequencies. It has to be of a certain frequency before you see this effect happening. So it has to be basically done with a UV light, like we see here. So the process by which electrons leave the surface of metals when light is incident on it is what is called photoelectric emission, and the effect of it is what we see as the electrons fly out from that metal. Now, like I said, entering into the 19th century, we had this problem of light. There was a debate between Mr. Newton, who was a British man, and Mr. Huygens, who was a Dutch. These two guys had a bitter debate on what is actually the constituent of this light. What we needed to know, that was the investigation in the early 19th century to see the nature of light. So some people needed to predict and see. So Newton predicted that light is made up of corpuscles or particles from his famous corpuscular theorem. He says that light is a corpuscle. Light is made up of packets or particles. That was his assertion from his famous experiment. And Huygens purported that the light is a wave, it's not a particle. So there was a challenge between Newton and Huygens, and the debate went on until even extended to other scientists that wanted to divide the kingdom, where some of them that went for Newton, some other scientists were supporting Huygens. So most of the scientists supported Newton because Newton seems to be getting most of his predictions correct. So people sided with him a lot. So we needed to know whether this light is a particle or is also a wave. So Huygens, for his own interpretation, said that if wave is emitted, you say every wave point on that wave front, like you drop stone in the water, you see the ripples. You see every point on that ripple, that is the wavefront, that is the particles that are of the same displacement from the source. So every point on that wavelength will serve as a secondary source to generate another wavelength. That was his idea, that this point will generate this generate this, and this other point will also serve as a secondary source to generate another wave here, another wave here, another wave here. So the wavefront keeps progressing, and that is what he said, that the wave move in this progression. So light behave like this. So light is a wave. So, and one of the properties of wave is that light must be reflected. Wave must be reflected. So he penetrated the light on a plane mirror, and the wave reflected back from that mirror. So from all his experiments, most of the scientists sided with Huygens that this is correct. Light is a wave because it's behaving like a wave like that. So it can be reflected. So Newton needed to show or debunk this. So he also wanted to prove that light is a corpuscle because he said that it's a corpuscle. So what is that? He brought a ball like this, and if this is now a packet of energy, according to Newton, they say light is a packet. So if I threw this ball onto the same plane mirror, which Huygens penetrated his own wave and it reflected. Let's say the floor is the plane mirror. So if I bounce this, you see the ball will reflect back. So that shows that light can also reflect. So this particle reflected. So Newton was correct also, because light reflected as the wave reflected in terms of the Huygens procedure. So there was already a big fight there. Nobody won there. So needed somebody to see who is actually right here. So not until early late century, this experiment, actually this challenge took place in the 17th century early. So late 18th century, somebody needed to bring up something to see whether these two gentlemen who is right. So it was Thomas Young who did his famous double slit experiment. He brought a slit and separated the slit with a distance d there, and he knows that if I penetrate light, considering it as a wave, the wave from that particular slit will interfere with the wave from this other slit. So this wave from here and this wave from here will interact, and interference will take place. That is, the crest of one wave will combine with the crest of the other wave, and when that happens, we know constructive interference will occur. And when constructive interference took place, the picture on the screen was that this wave gave, let's say that's the middle of the screen, that's x equals that. When this wave was incident, they saw where the constructive interference took place. We have series of bright and dark fringes. Where the constructive interference took place, the two waves emphasized each other, and they showed a bright light, which was called fringe on the screen over there. So we saw a bright light there, and where destructive interference occurred, we saw no light, that is destructive interference. So we have dark fringes and bright fringes, dark fringes on the screen. That was because of the interaction or the interference of the wave from here, the light wave from this slit and this other slit, and he was able to relate the wavelength of that wave as d sine theta, which means that the more I move away from this, I increase the angle between them. Let's say there was an angle between them. So if this wave goes that way, the force maxima, let's say from that point, and we'll have the second maxima somewhere here. So we'll have force maxima, have second maxima, let's say. So now there was a link between the angle, let's say this was the angle, so the angle between them, that is theta. So as I'm increasing from the force maxima, the angle increases. That's how the wavelength also was interrupted because of the order of the maxima appearing. The first maxima was m equals 1, and this one is m equals 2 as I was moving out. So he has to do that equation and found out that this angle, as I am increasing the angle here, that's how this x, which is the position of the first bright light, was also affected. So at smaller angles, sine theta, because if this is now L, let's say the distance between here is L, so at small angles, you will see that this length here, which is the hypotenuse, becomes this. So when that happens, this distance, this is x, that is the first position of maximum, the first bright light and the second bright light, and so on. So the x was the position of the light on the different on the screen at different position based upon how the angle was changing. So if you change the angle, you will see that the position of the x changes. So now he needed to link up this angle with if you assume that this hypotenuse of this triangle is now equal to this adjacent. So what will happen? Let's say this was L. So to a point where this L now becomes equal to this at small angle, instead of saying tan theta was opposite all over adjacent. So if I make sure that this hypotenuse is equal to this distance, that is the adjacent, that is at smaller angles, you see that this hypotenuse equals to this adjacent. So when that happens, the tan theta becomes equal to the sine theta over there. So we put them into that equation. You see that equation magnifying into, instead of d, now you have x over L. So you can find the displacement of that fringe L over that. So now we have the first position of the bright light was identified by him. So the whole thing here was leading to what happens to the interaction. It was an interaction. The incident, the light from this hole here and the light from this hole superposed, and interference took place. So that was why we saw fringes. Those fringes, just bright light, which was the fringes that were there, could not have appeared if there was no interference. So the double slit experiment now proved Newton wrong, that Newton's perception about light as being a particle is wrong. It is actually a wave, because the double slit proved that one here. So Newton was presumably defeated somehow, but somebody needed to rescue him. So see what happened in the early 19th century, let's say, two gentlemen, Davison and Gamow, also tried to do the interference, you know, and before that, they needed to use the electron here. Slit use light, but Gamma and Davison, they use the electrons, and they found out that the electrons also behave and passing through a particular crystal through here. So they penetrated the electrons through there, and the crystals, the spaces between the crystals of that graphite was what served as the slit over there, and the electrons that passed through those spaces also incident on the screen, and they found out that there was an incident pattern that also gave the same fringe pattern that double slit that Young discovered here. So we can assume that electrons also behave the same way this light behave here. That was the conclusion, that if electrons, which was considered as a particle in our previous discussion, now has behaved like a wave here, then we can say that the wave also can also behave as a particle, conversely, because that was the understanding. So if the electrons behave as a particle, from this experiment, it verified. It was actually, they repeated the slit, double slit experiment, those two gentlemen, Gamma and Davison, and they were able to see the same result as what Slit did. But the only difference is that they did it with the electron, and they found out that there was a slit also, there was a fringe appearing here, fringe appear here, fringe, and fringe only appear when there is interaction, that is interference. So it means that electrons, which was considered as a particle, is now behaving as a wave, and this wave, which is the light, as we presume to be light according to this double slit, has also a particulate property. So we can say light has duality, so it can behave as a particle, as the electron, which was considered as a particle, now behave as a wave. So this light also can also be a particle. So it needed the champion to actually verify that. That champion was Mr. Albert. So see what he did. Albert now needed to explain something to them, that you have got a clear evidence that this light, which we considered as being a wave, is now behaving as a particle, because electron, which was considered as a particle, now behave the same way as light. So we can now purport that light can behave as both particle and a wave, but somebody needed to convince that. So it was left with Albert Einstein to explain all of that. What he did was that he shined, that was a metal, he shined light onto that metal and discovered that. See what happens. When he shined light on that metal, he discovered that electrons were flying away from that metal. So now, electrons flying away from that metal was one of the rescue to prove that light is not actually only a wave. It can exist as a wave and also as a particle. So see what happened there. After these guys, Heinrich and Wilhelm also did the same experiments, but Albert was the one who explained it very well. See what he did. Now he said that below a certain cutoff frequency, where after penetrating the light, it is not all light that will emit the electrons. It is not all the light that has that energy. The light must have a specific energy to be able to emit that electron from that metal surface. So electrons will leave that metal surface when light is incident. And that light that is coming with a frequency of that, let's say, according to Planck's, that light coming is a light. Now when it's incident on this metal, electrons left. And this electrons leaving was due to the fact that the light that came in was containing energy. That energy was the packet of energy. And what happened actually was that the energy contained inside that light, photons, which he called, was given to the electrons. And the electrons receive much energy. If you have enough energy such that you can break loose from here, just like the example here I want to show you. Look at what happens here. This is actually the electron that is bound onto it, that metal there. And now the light was incident on that metal. That's the metal, the blue stuff is the metal. Now the light is incident on that metal. What happened was that if the light has enough energy, it has the ability to remove this electron from this metal and bring it at the surface here. That is, the ability of this light must be able to overcome a certain frequency. That frequency is called the threshold frequency. The frequency of the light below which no emission, the frequency below which no electron can be removed. Because if you now don't overcome the threshold frequency, then you are not going to allow the electrons to move. So that threshold frequency is FO, and that threshold frequency is only when the energy of that light was given to the electrons, and the electrons in that hole is also called showing the size, the measure of the size of the energy of the hole. So the size of that hole tells you what happens. So now that was the threshold frequency. The work function. What's the work function? That was 5. That work function, it's the least energy required to remove the electron from this hole and just put them on the surface here. So that energy required to remove it, if actually showing the gap, that is, like I said, the work function is actually measuring the size of the hole, because it is telling you the least energy required to remove the electron from that metal, first of all. It has not gone out here, so we cannot talk about kinetic energy. So in that case, the kinetic energy is 0. So Albert reasoned that if the electron is coming with that energy, which is HF, then what will this energy do to the atom, to the metal there? The energy from this is given to the electrons. You have to remove them from this hole. The electrons will move from this hole like this, and that is the energy required there is called the work function. And when that light that is coming has enough energy, giving it to this electron to move from the hole. Now they have moved from the hole, that is the work function. Energy required to move the electron from its parent atom. Now what will happen? It needed to move. So that energy that is moving the electron that fly away, as you see them there, is what he referred to as the kinetic energy. So now the energy of the light I'm bringing here, that energy of the light incident here is capable of removing the electron from that hole first there. That is the work function. And now if the energy is enough, this electron is giving excess energy, and that electron will be able to fly away from that metal surface. That is what Albert Einstein tried to explain. That the photons, which is the packet of electromagnetic radiation, that is the photons. Albert now concluded that the light that we are talking about here is not just a wave. It is coming in the form of a packet, and that packet is called the electromagnetic radiation called photons, and that photons have an energy which is equal to the frequency times the Planck's constant. Remember that? That's the energy. So now we now know the terminologies here. So if the threshold frequency is not overcome, then the electrons cannot move. So it means that as the energy is coming there, never mind you have the work function and you have the kinetic energy. If the electrons cannot move because you have not exceeded the threshold frequency, then this guy goes to 0. So what will happen? The energy of that guy is now going to be equal to the threshold. It's going to be equal to the work function because this one goes to 0 already. So what will happen to this? It's going to be this equals this. So that energy for this is called the work function. So if I want to find the threshold frequency, I'm going to have threshold frequency as equals to that. And that frequency is what matters there, because if you don't exceed threshold frequency, there is no electron that is going to be. That's why we call it the minimum frequency required for below which no electron can be removed. And work function is the minimum energy required for electrons to fly off from that surface. And photons is the packet of electromagnetic radiation that is required to do this experiment. So Albert Einstein was the one that explained and was able to support the view of Newton that actually light is not only a wave. Light can also behave as a particle, and that is the one prediction. So for your objective, you'll be asked which phenomenon explain light as a particulate property. It is the photoelectric effect shows light as a particulate behavior, meaning light exists as a particle. So that is what was shown here by Albert Einstein. So let's see what he brought up again. He was able to explain, so nobody explained it, why that thing happened, but Albert Einstein was able to look at the problem. If you look at the last paragraph, you see he made an assumption that had been made by Isaac Newton already. And what was the assumption? He said that the light acted as a particle, just like what I told you here. That's what Albert concluded, that the light actually acted as a particle, because it was like that particle. Because if it was a wave, all the wave was just coming with one energy, and the electron would have just been flying there. But the electrons did not fly until when enough energy was incident on that electron, and the electron gained enough energy. So it means there's a packet of energy that you require for you to actually move or fly away from that metal. So, and the observed energies can be explained by Planck's law there. That was what Planck gave us. And you can see from his experiment there that if this is equal to HF, and we know that light is having speed, relationship between speed and the light, the speed of light and the frequency. So you can find the frequency as c over lambda. So this equation now gives you, instead of that, I'll put c over lambda. So we can now infer that the energy can be calculated in terms of the Planck's constant, the speed of light, and the wavelength also, as you see from that board over there. So let's see. Now, actually, Planck first applied his quantum theory to light trap within a box, stated that it acted as a particle, but he still theorized that light was a wave outside the box. So outside the box, light was a wave. Inside the box, light appears as a particle. So that was what Mr. Planck concluded, and you see that Albert Einstein also expanded the idea. Albert Einstein expanded it, and he said that light acts like a particle. So we know that previously that light was a wave. Now we have confirmed that light acts as a particle through this photoelectric emission, and he stated that light is a group of photons which acts as a particle. So that is the particulate conformation. So let's see what came out from the photoelectric effect. Now, the quantized nature of light explains both phenomenon. Watch, the first one is that electrons are emitted only when the light frequency is higher than a certain value. So that is what I told you, that you must exceed the threshold frequency. When you don't exceed the threshold frequency, the light is, the energy of that photon does not exceed the threshold frequency. There's no way you expect the electrons to fly away. That must be one thing. So you must have a certain value beyond which you can see electrons move. Below it, no electrons move. That's called the threshold frequency. Now it says that the energy of the electron is not continuous. That's what was predicted. So the energy is not continuous. It is of a discrete value. That's the more reason why we say it's particulate. It contains particles. So light must be traveling as a packet and specified sizes called photons, and the electrons are only emitted when this single photon strikes that an electron there, and all the energy of the single photon is transmitted onto the electron, and the electron is free from its orbit and is able to exist and fly away, and that moving away is kinetic energy. So you needed extra energy to move and fly away from the metal. So that is what Albert Einstein. So let's take some questions here. Watch out from what I have said. I said, what is the energy of the photon with a frequency of 5 times 10 raised to the power 22 hertz? So watch that. So the first question there, question 33 says E is HF. You say, what is the energy? So you know that Planck's constant is 6.63 times 10 raised to the power minus 34 Js. And this question, the frequency is 5 times 10 raised to the power 22 hertz. So if you punch that from your calculator, you have 3.32 times 10 raised to the power minus 11 is joules. That is the answer for that question. So let's proceed to the next question. Watch out. It says, what is the wavelength of a photon with the energy 5 times 10 raised to the power minus 11? So what is the wavelength? You say, this time you're talking about the wavelength here. So remember, C is frequency lambda. So now we can find frequency as C lambda. So I can put it right inside that equation. We have, this is Planck's constant there. So instead of that C, I put this. So now our question is to find the wavelength. The wavelength is going to be hc over E. So h is Planck's constant, given as 663 times 10 raised to the power minus 34. And the speed of light is 3 times 10 raised to the power 8. It is 300 millimeters per second. And the energy is given there as 5 times 10 raised to the power minus 11 joules. Now if you punch that from your calculator, you'll be able to find the wavelength as 3.98 times 10 raised to the power minus 15. It's wavelength, so it's measured in meters. So that's the wavelength. You must be able to do that here. So we'll look at the other one there. It's if the wavelength of a photon is cut off by half. So look at this question. Now I've just explained the photoelectric emission for you. So now let's try and see how we can use it. You see, if we cut off the wavelength of the, so watch here, this is H, is hc over lambda. So if I cut off the wavelength by half, so I have E. So what this is, let me call it the EO. There, that is the energy, original energy. Now, what if I come to cut off the wavelength by 1/2? So I have hc all over, this is 1/2. So what I've done is to substitute this, divide by 2, that's half there. So I have now, if I do the math, you have 2 into hc all over lambda. But we already know that this is this. So we can see that the energy now becomes twice the energy of the original. So we have you'll be able to see that answer there. The answer is twice that. So you can even see it from the mathematics. The reciprocal of half. The inverse of half is 2, you know that. So now we have the ratio of the energy to the frequency of a photon is given by that from our equation was here. You see the ratio of the energy to the frequency. So energy to frequency will give us the Planck's constant. The energy to the frequency gives us the Planck's constant. So we have the question there. I'll read it for you. A, the options. You see the ratio of the energy to frequency for a photon is A, its amplitude, wrong answer. B, its velocity, wrong as well. C is Planck's constant, correct answer. And D is its work function. So the correct answer is Planck's constant C. So we get it. We get the next question says, what is a photon? I just told you that Albert Einstein was able to discover that the light will now behave as a particle, and that packet or quantum of that particle is what was referred to as the electromagnetic radiation called the photons. So photons was a packet of electromagnetic radiation, and now we can read the options again. What is a photon? An electron. A says an electron in an excited state, wrong answer. B says a small packet of electromagnetic energy that acts as a particle. That's what Albert told us. B is the correct answer. So that is. Now, we go to the next question. Says the energy of a photon depends upon, watch out, I said that when the light was incident on that metal, it is the energy, the kinetic energy of that electrons that is going is independent upon the intensity of the light. Watch out for objective question. The kinetic energy of the electrons that are flying, the photoelectrons, is independent of the intensity of the light. What it's dependent on is actually the energy of the photon is dependent upon the frequency. That's what Mr. Planck told us. So the energy is dependent upon the frequency, is directly proportional to the frequency. So A, its amplitude, B, its velocity, C, its frequency, correct answer. C is the correct answer, its frequency. The energy of a photon depends on its frequency. That's correct. So we look at the photoelectric effect was explained by treating light as what I've said so far. I said before the big debate assumed that light, according to Mr. Newton, light is a corpuscle. According to Mr. Huygens, light was a wave. Now we needed somebody to confirm that, and we said from our discussion, the double slit experiment proved that light is a wave. You know, it seems to go against Newton. But after this photoelectric effect, which was now purported by Albert Einstein, that light was behaving as a particle, because it's only the particle district bundle of that particle that had the energy, and that energy was directly proportional to the frequency of the light. So the question says the photoelectric effect was explained by treating light as a particle, B, wave, C, a wave and a particle, D, none of the above. The photoelectric effect was a phenomenon that confirmed that light is a particle. So we have the A as the correct answer there. The photoelectric effect was explained by treating light as a particle. So A is the correct answer from our experiment. So look at these terminologies. I've already discussed them. First, they said threshold frequency is the least frequency below which no electron will be removed. I just explained that in my experiment. And work function is the least or minimum energy required to remove the electrons. It is actually the measure of the hole where the electron is coming from. And I said that it is, according to Albert Einstein, it is the energy of the incident electron. If we subtract the kinetic energy from it, then you have what is called a work function. So that was the work function formula, if you like, or you can say E is equals to phi plus Ke. So if you do the math there, you will see what I'm saying. So now work function was that. I say. So now we go to the next there, which is the photo theory of light. I just explained that to you, so we can see it briefly here from what Albert Einstein actually purported. Different frequencies, and compare it with the maximum kinetic energy of the electrons as they fly off. So now he was able to plot a graph against the kinetic energy and the frequency. So after penetrating different frequencies of light on the mirror, on the metal, he found out that the kinetic energy was changing. So he plotted the graph against the two. So he found out that at some point here, up to here, no electron was moved out. So that's point where no electron was. So all here was like the photon was doing work against the well. That is the energy required to remove, the least energy required to remove. So you have to exceed the threshold frequency before electrons start flying. So when he plotted the graph, he was able to see that now beyond the threshold frequency, electrons begin moving. So we can have the kinetic energy of the electrons as they are increasing now, as they are moving in that order. So he was able to plot a graph that way. And that graph, the gradient of that graph will give you the Planck's constants there. And this point here is giving you the threshold frequency. So if you compare this with a straight line equation, you have mx plus c. So you have on the y-axis you have the kinetic energy, and on the x-axis you have the frequency. That's the frequency over here. So you now have the frequency somewhere there. So now if you have the 2, you now say the gradient is that. So you have plus or minus phi, and you can see how phi came in here. So if you project there, you cut against here, so you have a negative value for phi if you project the line extrapolated. So now we can see that this energy is given by that. So see what Albert Einstein did for us. The graph cannot be explained by the wave theorem of light. That's we have to go to the particulate theorem of light. So this shows that light is made up of particles, photons. Light is not a wave. That is what this graph shows you. So the different kinetic energies we are plotted against the frequency, and it gave a straight line. And if you compare the equation of a straight line, the gradient of that line will give you the Planck's constant, and the point where the graph cuts the f-axis, which is the x-axis, that part gives you the threshold frequency. You can find out that from all this shaded part, there was no electron. So we can't talk about the kinetic energy because the energy was not enough for the electrons to fly. It was when you exceed the threshold frequency, now you expect the electrons to begin to fly. So you have kinetic energy starting from here. But all here, it is what gave rise to that Planck's constant. And that Planck's constant was achieved only when the threshold frequency is a constituent of the threshold frequency. So we now know that. Now we see how the photons also, the graph below, this is the same graph, it will emit electrons with a maximum kinetic energy. But notice that the y-intercept of the graph below, you say, what does that mean? The x-axis, if you go back to that question, you see it will emit electrons with a maximum kinetic energy. But notice that the y-intercept of the graph is below the x-axis. So that's just what I was trying to emphasize here. What does that mean? The work function is a negative quantity based upon that equation over there. So that is it. So Albert Einstein's photoelectric equation was the conclusion. That was his equation, that when they learn energy, the light came with that energy. It used part of that light to remove the electron from the metal. That's called the work function. And the excess of the energy was given to the electrons to move. So the photons, the energy of the photons is equal to the sum of the work function plus the kinetic energy. And if you do the math there, you will see what will come out of the kinetic energy and so on there. So that is Albert Einstein's photoelectric equation, and you can see it further there. Watch out, I've said something about all of this. Now you have one question to answer even as we leave. The photoelectric cell has a work function of that. They say, what is the minimum frequency of the incident radiation? You're talking about minimum, so you talk about here, the work function is given to you there. You say the work function is there. So minimum frequency is the threshold frequency. So what is that threshold frequency? It is the work function all over Planck's constant. So the work function is given here as 5 times 10 raised to the power minus 19, and the Planck's constant is 6.6 times 10 raised to the power 34. If you punch that from your calculator, you have 7.5 times 10 raised to the power minus, 14 Hz. So that is the frequency. That's threshold frequency, of course. So now you get the assignment above. I'll read the assignment for you. Now light with a frequency of 9.5 times 10 raised to the power 14 Hz is incident upon a photoelectric cell with a work function of 5 times 10 to the power minus 19 joules. What is the maximum kinetic energy of the ejected electrons? Take Planck's constant at 6.6 times 10 raised to the power minus 34 Gs. So that is your assignment. So we're going to stop the lesson here, and you watch out for the next lesson. Make sure you do the assignment. Thank you for your audience.